This all started when I left school, not really quite knowing what I wanted to do, but I was good at maths and technical drawing and so on. And I ended up in a small firm in Westminster. And I can remember walking through the door thinking, yeah, this'll do. The firm was very small, there were only 4 of us. The boss was frequently away on holiday, and he left us some work to do, but when we'd finished that, we could do what we liked. And I spent my time in Westminster Library, and that's really when I started my education. It's there that I became fascinated by the remarkable group of engineers who were doing such extraordinary structures. Taroka, Nervi and Candela. And they were producing structures which I could tell were well beyond the analytical abilities at the time, and so they were the result of remarkable courage and judgment and so on. So when I finished my time with the firm in Westminster, I applied to the UK equivalent, which was the Over-Arab Partnership. I was interviewed by Peter Dunnican, the managing director, and he asked me what I wanted to work on. And I said I had to work on something interesting. And I spent the next 3 years working on the design of the Sydney Opera House shells. I was in a small team led by a Danish academic called Hugo Muhlmann, and the second in command was Peter Rice, who, as we know, went on to be a very famous engineer who very sadly died young. As we all know now, after 3 years, the solution was discovered. Not shells, but pre-cast, pre-stressed units, rather like the segments of an orange, laid one on top of one another. I decided I could see a future drawing sections through precast units. So I decided that I wanted to test myself academically against other people. Up until then I'd been studying an HNC in civil engineering, which at that time was the equivalent of a degree as far as the institutions were concerned. There were only 2 postgraduate courses around at that time. One was at Imperial College and the other at Leeds University. Imperial turned me down straight away, of course, no first degree. But Leeds liked to have people on the course who had practical experience. And so off I went to Leeds, a very cold city after living in the soft underbelly of the south. So on the course, my first experience, full-time education, having a good time. Course was difficult because there are lots of things that the other people on the course who had honours degrees generally knew that I didn't know. So I had to do a lot of studying by myself. Halfway through I thought I'd like to stay on, do research. So I applied to the head of the department and he told me I couldn't, because I didn't have a first degree. So I looked around the world and was eventually accepted at the University of Arkansas. Took the papers to the professor, a wonderful man called Professor Evans, and asked him to sign the papers. And he said, well, why don't you do it here? Why don't you do it here at Leeds? So I said, well, I haven't got a first degree. And he said, oh, don't worry about that. Now, what I didn't know, and I never really found out why, but he was the Pro-Vice Chancellor and decided to back me. Now, the problem was that because of this rather unusual route to research, I had to work with the member of staff who was the most difficult, a Polish lecturer called Albin Kronowicz. Now, I've got some Polish history, so he and I got on absolutely fine. But the problem was, his subject was cylindrical shells, and that was very tricky in terms of the maths. Anyway, eventually I got it sorted out, and found that there was a computer on the site, one of the first commercial machines of Ferranti Pegasus. As a lowly civil engineering postgrad, I could only get it there at 3 o'clock in the morning, so I'd stumble down there with my punch tape, and of course it never worked. But eventually I got it to work, and I could do some calculations and compare the results of the experiment. The shells I was testing were 2-meter span cylindrical shells, which were a popular form of industrial roofing at that time, and my task was to investigate the significance of changing the depth of the edge beams. I decided to focus my attention on the longitudinal stresses, longitudinal tension and compression, and the displacement at the center of the shells. Other studies had looked at the transverse bending moments, but they were so small that they were the order of magnitude of the errors in the measuring equipment, so I didn't bother with those, and I was measuring using strain gauges and DMET gauges, and eventually we'd finished the first set of results for the first shell. When I came to compare them with the theory, I got a terrific shock, because there was a massive difference between the experimental value and the theory. And this is really the point of all this in this business of understanding structural behavior. I thought I must have made a mistake in the experiment. I thought, hold on a minute, it's just a bit of concrete being loaded. It doesn't know it's part of a research project, so perhaps it's something else. I then looked at the papers that have been published on the same subject by the Cement and Concrete Association, who were the major advisory body for the concrete industry. They'd run an experiment on a much larger shell than mine, but they'd got the same results. And they'd put the error down to experimental error. Because, of course, when you're measuring stresses in concrete, you measure the strain and convert them into stress via another specimen which has been used to determine the modulus of elasticity. But when I looked at the displacements at the center of the shell, there was still the same massive difference between the two. So I looked at the published paper, and I discovered that they got exactly the same differences as I had. But they put that difference down to experimental error. But when I compared the displacements at the center of the beam, there was still the same massive difference, and they had no doubt discovered this, but they hadn't published it. So I rang him up and said, I'm doing something similar at Leeds, where's the low deflection curve? And there was a long silence and a pause and a shuffling of feet, and I thought, yeah, they've discovered what I've discovered, and for which there is no explanation that makes any sense. So I was able to fiddle about with the formulae which connected the shell to the edge beams, and eventually I discovered that it was far too simple, and by adjusting various factors I got the two to match up. But the point of all this is that it is from that point onwards that I never trusted the results of structural analysis.